at the turn of the century, people were studying these things. They're called black bodies. And so they are some sort of object. It's a theoretical object. The idea that any light that hits it is absorbed, but then it's also emitting as well. It's a perfect absorber and emitter. And the definition is such that the wavelengths emitted are only dependent on the object's temperature. All right. So what does that mean? That means if I look, if I can figure out what I have my little detector here that's connected to a computer. Here's the old, I don't even know what, connected to a computer. And if I can figure out what this wavelength is, right? Wavelength from the object is blah. Right? I immediately know what the temperature is. So we talked a little bit about this, right? During that was with on the Gaussian curves with the Maxwell's curves, where we talked about this as well. So there was a guy, Max Planck. There's a C in there somewhere. He's a nice German dude. Max Planck was trying to Max Planck. Sounds like a cool punk band. Was trying to figure out what else can I do? Can I predict the temperature from this wavelength? Like, what's a good prediction? Rather than just having a chart, can I do some other things around what's happening there? How do I get some math to describe what's happening here? Rather than just saying this is the relationship, how can I describe what's actually happening inside of here? Well, light is a wave, and waves are created, right? Waves are created by things vibrating. So Max is like, okay, I think, right? I think trying to understand this solid, this is like early 1900s, might even be late 1800s. What is happening here? How can I describe this object? And his perspective was that this object was continuous, and that trying to do looking at this as some solid piece that was where it was all just kind of like the same thing was too hard to do the math with. So to make the math easier, Max cuts black body into tiny chunks and then integrates across the tiny chunk. So here's this piece, here's this piece, here's this piece, here's this piece. Here's this piece. Here's this piece. Here's this piece. He made tiny little pieces, tiny pieces, and then he just integrates. So takes these tiny pieces, and then each tiny piece would emit only a set chunk of light. Because remember, the spectrum that's coming off of here from our Maxwell curves is not, right? It comes out, here's our wavelength, and here's our number. The number of power, I guess, is probably intensity. So you have cold things, or cold things come up like this. Warm things go off like that. So I'm emitting each one of these. So he took the frequencies, chunked it all up, and said this little chunk is emitting this one. This little chunk is emitting this one. This little chunk is emitting this one. Just to make the math easier. And so the amount, the total energy, so the energy of each chunk is going to be some, it's going to be some frequency. And then just to make the math again, right, that's all I'm going to do. Each chunk is going to emit some frequency of light. And then I need this to be an energy. So I'm just going to put some constant out in the front of it. So chunk 1 is constant times frequency 1. Chunk 2 is the constant times frequency 2. He doesn't know what that constant is. He goes, I just need to convert it from frequency to energy. So it's got the units right. It is very much an ad hoc setup. All right. So because he knows his Latin, tiny pieces, right, that I can't get any smaller are tones that cannot be cut out. They are atoms. And they're vibrating, so he called them atomic oscillators. He started to do some math, and turns out this number started to actually like fall out pretty easily. He didn't use a constant, he used H for his constant. You know this as Planck's constant. The energy of that light that's coming out is just the frequency times Planck's constant. This is a setup of the universe. And I really want you to realize that Max Planck did not set out going, I'm going to figure this out. He's just trying to make the math easier so he can do the calculations on paper, because computers don't work yet, because Charles Babbage got bored and moved along and shoved some things in a desk. Bankers, they're the worst. So the energy of that photon, yeah, he totally just stumbles upon this. And he is really the first one to talk about this concept of the atom. So he, to make the math easier, cuts these things up into atoms and says, oh, they just all emit some little bit of light. Holy crud, I'm right. Right? I was just guessing. So that means, this means that energy is chunked. But because, right, nobody likes their energy chunky, the nice fancy word for chunk in Latin is a quanta, like quantity. So it comes in a quanta or is quantized. So don't really, I want you to think when you hear the word quanta or quantize, I want you to think of chunk. Rocky Road. So the energy of a photon that comes out of there is how much energy is it? It's just Planck constants. All right. Which leads me to my favorite pirate joke. What is a pirate's favorite letter? You'd think it's R, but it's C. But what he really wants is his I. And when he gets angry, he makes people walk the H. With that.
Oh God, that's bad.